from China is not good, or it's because of my microphone. I'm not sure.
Your microphone is okay. I think if you turn off your video, that will help.
Okay. How about now?
That's working.
Okay. Oh, good. Good. So I start from the first page, or I just continue? I continue, I think. So the first part of my talk is the work I did in mice, which is about NV-based magnetometry. So it is actually the vector magnetometry. It is generally interesting for various applications like detection of biosignals, earth field mapping, or minor source detection in geophysics, and detection of space magnetic field, and detection of condensed matter systems, or even single electron and nuclear spins in physics. There are also different kinds of vector magnetometers with excellent performances, like fluxgate, squeeze, and alkali vapor cells magnetometers. Here we notice that all of them, fluxgate and squeeze, typically need 3 sensors to get all 3 components of a vector magnetic field. And the nice commercial Q-spin magnetometers measure 2 directions of a field. We focus on magnetometer based on nitrogen vacancy centers in diamond because of the following advantages. It can work in a wide range of temperatures, no need of special environment. It is able to be fabricated into different forms like nanocrystals, nanopellets, thin films, bulk chips, etc. And it is chemically inert, biocompatible for living cells. So living cells can reset on top of a diamond substrate and can uptake a nano diamond without being poisoned. One of the most important advantages is it have higher spatial resolution than others, and it detects vector information field intrinsically instead of a projection of field. These features makes diamond-based vector magnetometer competitive. And probably you have known how NV centers work. In case needed, I still go through about its basic characteristics. In the diamond crystal lattice, it consists of a substitutional nitrogen atom and a substitutional and a neighboring vacancy. In other words, here a missing carbon atom. We use negative charged NV centers for magnetometry because it has spin 1 ground state and long coherent time. One can typically use 532 nanometer laser to drive the transition from ground state to excited state. Then the NV centers decays back to the ground level, emitting fluorescence in red color. When continuously illuminating the NV center, a high fluorescence intensity can be detected. On the other hand, if it is initially in one of the m equal to +1 and -1 sublevel, it will be excited to the excited +1 and -1 sublevel, which has a larger probability to undergo intersystem crossing to the single state and then preferentially decay to ground state. This means that the NV center emits less fluorescence in red color. So the spin state can be read out from the fluorescence intensity. They are typical diamond-based vector magnetometry using ODMR technique, optically detected magnetically resonance. So magnetic field coupled to the NV center through the Zhiyin effect. This figure shows the energy as a function of the magnetic field along the NV axis. So NV centers, which is initially prepared in m equal to 0 states, can be driven to +1 and -1 spin states by applying microwave fuse. Then a drop in the photoluminescence signal can be observed at this resonance frequency. The magnetic field along the NV axis can be detected from these different resonance frequencies. And since there are 4 possible ways that the nitrogen atom positioned with respect to the vacancy, so leading to 4 possible NV alignments. So for a magnetic field in an arbitrary direction, each of the 4 NV axes has a different magnetic field projection, resulting in 8 ODMR peaks. Then from these peaks, one can reconstruct the vector magnetic field. Considering there is some applications which don't like those microwaves, we propose a new method to use NV centers to detect the vector field. This technique is to detect spin population transfer under the field perturbations at so-called G-slag region.
I stopped the Zoom using my microphone. So it worked well now?
Yes, it is. Please.
Oh, nice.
Great.
Great. I'm sorry for this trouble. It takes too much time. So I should continue from here, I think. So I just repeat again on this page, or I jump it. I think most of you maybe didn't get this. So I repeat, okay. Considering there are some applications which don't like microwaves, and to overcome some drawbacks of ODMR vector magnetometer, we propose a new method to use NV centers. This technique is to detect spin population transfer and the field perturbations at so-called G-slag region. In a background field about 102.4 millitesla, there is a complex anti-crossing between ground state and Zeeman sublevel. This figure shows the energy levels considering the hyperfine coupling between the electron spin and the nuclear spin of the near nitrogen atom. In this region, the energy gap is small, so perturbations can be easily made, resulting in population transfer between these states and resulting in a visible drop in photoluminescence signals. If we scan the field from 0 to more than 100 millitesla, we can observe this remarkably sharp feature around G-slag. In this figure, the magnetic field is along the NV axis, which is defined as the axis in our case. To narrow this line width of this G-slag feature, normally to optimize the sensitivity of magnetometer, the 100 millitesla biased field need to be aligned along the NV axis well. Then we find that this contrast itself also related to the angle between the field and the NV axis. As shown in this figure, we measured the features in different longitudinal fields and transverse fields. It can also be demonstrated by analyzing the Hamiltonian of this two-level system. So we can see here is another similar Lorentzian curve. when transverse field change. Therefore, near the G-slag, the photoluminescence signal and its derivative signal can be used to detect both longitudinal field and the transverse field. So we use typical methods to measure components in the axis by applying a modulation field modulated at a specific frequency, and they then demodulate the PL signals. So as shown in this figure, in this region, it is linear corresponding to the field changes. And for XY plane, which is transverse plane, instead of using another two modulation fields in X and Y axis, we actually applied circular modulation. It's a constant transverse field rotating along the Z-axis. We call the PL G-slag feature sensitive to transverse field is symmetric on XY plane. It can be simulated as a Lorentzian function curve rotated around the axis. If the external field has no transverse components, a circular modulation field on XY plane with a proper amplitude will result a circle sliced from the 3D Lorentzian. And if there is a transverse field, the circle has a biased center and the PL signal amplitude changes according to the time varying value of the modulation field, leading to a non-zero locking amplifier output. The phase output of locking amplifier actually reflects the angle between the target field and the defined X and Y axis. By this circular modulation, this method can avoid the crosstalk between X and Y axis because of two linear modulations. This is the schematic view of the experimental setup. The NV is pumped by green laser and the red PL signal is detected. We applied the modulation field in Z direction and XY plane through a small Helmholtz coils inside the electromagnet for G-slag. The demodulated PL signals from locking amplifier are collected. Here we use a Japanese-made sample. This is the properties. To give a direct impression, the dimension of the sample is less than 1 millimeter in each direction. Here we first use a typical method to measure vectors in X and Z plane by modulating Z and X with two frequencies. We can see again a linear relationship between the demodulated signal and the BX. This is the measurement results. We show the ratio of measured BZ and BX, BZ over BX, corresponding to arc tangent curve, which means this method is effective. And again, we measured a matrix of field vectors on X and Y plane. So the upper two are simulated ideal results. The arrows in left figure is the field vectors and the color represents the field amplitude. And the red figure shows the field vector angles in those different points. And the bottom two are measurement results showing a good agreement with the simulation. As a demonstration of 3D measurements, we applied a series of magnetic fields in 3D spiral shape. The red arrows shows the measured results, which is normal to the sphere. All three components are compared with the applied magnetic fields here. Also, we also attach the arrow bars of the angle of phi and theta here. The noise floor of axial direction is measured. The magnetically insensitive noise is around 300 picotesla per root hertz. The photoshot noise limit is calculated to be 65 picotesla. And this is the noise spectrum of transverse axis, showing the similar noise level. And the decrease for the frequencies above 1 kilohertz is due to the filtering of the locking amplifier. So a quick summary of this part work. This vector magnetometer don't need microwaves. Direct readouts 3-axis field components simultaneously, and it's free from systematic errors during reconstruction in ODMR techniques. And there is no crosstalk between x-axis and y-axis in xy plane. And it can be extended to single NV probe. For further improvements of better sensitivity, there are several aspects. For example, better photo collection and other readout methods reduce inhomogeneous broadening because of local magnetic fields, potentially arising from string electric field and steam baths and so on. Of course, good samples with narrow line width is always important. The second part of my talk is what I do in Harbin Institute of Technology. I said after COVID-19, I came back to China, and maybe in the beginning I said this, maybe my voice is lost during those slides. So we built an environment with nearly zero magnetic fields in Harbin Institute of Technology. The aim is also for detecting weak magnetic signals. So this is the background of the project. I took some parts from our institute's introduction video to share with you. So the Earth is floating in the vast universe. When we look up at the sky, the questions like how the universe is formed and whether humans are lonely have inspired people infinite explorations of the universe. These thousands of spacecraft operate in space help us explore, understand, and use space. However, the space environment is extremely harsh and complex. The reliability and life of the spacecraft are seriously affected. The safety and health risks of astronauts have significantly reduced their ability to stay in space. So the interactions between the space environment and the spacecraft are still an open question. This is the actual building where I am working now. Based on these backgrounds, what we want to build is a space environment simulation and research infrastructure in the new campus, with the short name of Space Station on a Ground. By simulating various space environment factors and effects on the ground, the influence of those environments on materials, devices, systems, and living organisms are studied. So our department is located in a new district of Harbin City. The infrastructure itself has a total budget of 1.5 billion yuan and gets an area of 360,000 square meters from the government. We will build the infrastructure in this new campus. And it includes a space integrated environment system, a space magnetic environment system, a space plasma environment system, and a numerical simulation system. So the space magnetic system is what I'm working on. Until now, we have finished all design of different parts of this system, and we built them together to cross-check if there is any interferences. The right side is the target performance. The shielding factors in the central volume of 1 cubic meter is 100,000, and the residual DC field is less than 0.2 nanotesla. It includes IF shielding, active shielding, heavy passive shielding, MSR, and coils for field generation inside MSR, and an anti-vibration floating platform, and other support subsystems. Here, the photo was taken when the anti-vibration platform has been finished, this one. It has 8 meters length and can reach 1 micrometer stability to avoid the magnetic noise due to vibration. And the RF enclosure was also finished. Here, the first part of the coils is active coils out of the MSR. Those blue lines on the photo. I just talk it quicker since it takes too much time at the beginning. So the coil and the RF layer was coupled, has coupling effect, making normal coil have different field amplitude. The normal model to consider this coupling effect is a mirror model. I think all of you have known this. We know that if one thing placed in between 2 mirrors, then it will be imaged for infinite times. So one researcher in our group, my colleagues, proposed a mirror model to consider this kind of influence with lots of times of images. This is the coil, this is the shielding layer. And the restriction of his model is still assuming the shielding layer has infinite thickness. But we designed the active coils by this model. The measured amplitude of this blue active coils has already done, and it is agree with this mirror model. And the second part of the coils on the MSR means the degaussing coils of the shielding. And we know that, maybe when you know that the residual static field inside the shield is determined by demagnetization process instead of the shielding factor, because the shielding materials has remnant magnetism. So here I propose a dynamic model based on Gell's accident hysteresis model to understand this process. One good example is that one layer of our MSR, it was just finished in the factory in this month. After demagnetization, the DC field has reached 30 nanotesla. It is more than 1,500 times damped compared to the external earth field. And we demonstrated that by optimizing the degaussing coils into distributed coils, the lowest field was achieved with a certain degaussing sequences. It is also the most stable field we had measured until now. The performance is during the nearly 10 hours in night. The change was less than 20 picotesla in all 3 axes. More details can be found in these references, since we have the time is very limited now. Then the third part is coils inside the MSR for field generation. It has the same coupling effect to the shielding layers. So here we built the calculation model use surface boundary conditions. In COMSOL, it means magnetic shielding boundary condition and transition boundary condition for AC field model. And we also use equivalent μr of the shielding wall to consider the complex structure of the layer made up made up of new metal strips and air gaps. So here is a comparison of the simulation result and the environment result of a Helmholtz coil inside BMS R2. With a model of 2 layers, the calculation results already agree with the experiment. And then one PhD student in our group proposed a new model to improve the mirror model of coils inside MSR by considering the thickness, the shielding layer has a certain thickness. It agrees with both FEM results and environment results. More details can be found in this paper. So in the last, these are my colleagues in 2 groups. Thanks to them, and thank you for your attention. I'm very sorry for the trouble at the beginning of the talk. Is there any questions?
Sure. So in your diamond vacancy magnetometer, you say that you don't need microwaves. What's the significance of not needing microwaves? Why is that a good benefit? I'm not familiar with.
One reason is in some biomedical applications. Some people say the microwaves don't have effects on people. Some people think there are effects, but we haven't have clear evidence. But here we propose this method to give another possibility. And also for some application which need very low temperature environment. For example, superconducting materials detection, then microwave will cause temperature changes. Yeah.
Thanks.